calculate the fault current from nameplate data, you can use the following formula: fault current in kiloamps equals primary voltage in kilovolts times primary current in kiloamps divided by 0.6. For example, if the primary voltage is 13.8 kilovolts and the primary current is 1.5 kiloamps, the fault current would be calculated as follows: fault current equals 13.8 kilovolts times 1.5 kiloamps divided by 0.6, which equals 34.5 kiloamps. To round the fault current to the nearest 1000 amps, you can use the round-up function. In the previous example, the rounded fault current would be 35 kiloamps. There is no standard distance for providing the value of fault current. It is usually given at the bushings of the transformer. However, it is possible to calculate the fault current at any point in the circuit by applying the appropriate impedance values. When calculating fault current, it's important to understand the underlying principles and assumptions. Firstly, the formula provided is a simplified approximation that assumes a certain level of system impedance. In reality, the actual fault current can vary depending on the specific characteristics of the electrical system, including the source impedance, cable impedance, and other factors. Secondly, the formula is based on the transformer's nameplate data, which represents the transformer's rated values under normal operating conditions. During a fault, the transformer's performance may deviate from these rated values due to saturation, heating, and other effects. Thirdly, the fault current calculation is typically performed for a three-phase bolted fault, which represents the worst-case scenario. In practice, other types of faults, such as single line-to-ground faults or line-to-line faults, may occur, and these faults may result in different fault current levels. When applying the fault current calculation in a real-world scenario, it's important to consider these factors and consult with qualified electrical engineers to ensure accurate and reliable results. It's also crucial to verify the calculations using appropriate software tools and to validate the results through field measurements and testing. In addition to the basic formula, there are several other factors that can influence the fault current level in an electrical system. One important factor is the transformer's impedance, which is a measure of its opposition to the flow of alternating current. The transformer impedance is typically expressed as a percentage of the transformer's rated impedance, and it is indicated on the transformer's nameplate. A lower transformer impedance will result in a high fault current, while a higher transformer impedance will result in a lower fault current. Another factor that can affect the fault current is the system voltage. A higher system voltage will generally result in a higher fault current, while a lower system voltage will result in a lower fault current. The system voltage is typically regulated by the utility company, but it can also be affected by factors such as load changes and voltage drops in the electrical system. The impedance of the cables and conductors in the electrical system can also influence the fault current. Longer cable runs and smaller conductor sizes will result in higher impedance, which will reduce the fault current. Conversely, shorter cable runs and larger conductor sizes will result in lower impedance, which will increase the fault current. The presence of other equipment in the electrical system, such as generators, motors, and capacitors, can also affect the fault current. Generators and motors can contribute to the fault current, while capacitors can reduce the fault current. The impact of these devices on the fault current depends on their size, location, and operating characteristics. To accurately calculate the fault current in a complex electrical system, it's necessary to perform a detailed fault current study. A fault current study involves modeling the electrical system using specialized software tools and simulating various fault scenarios to determine the fault current levels at different points in the system. The fault current study should take into account all of the factors mentioned above, including the transformer impedance, system voltage, cable impedance, and the presence of other equipment. The results of the fault current study can be used to select appropriate protective devices, such as circuit breakers and fuses, to protect the electrical system from damage during a fault. The protective devices should be selected based on their ability to interrupt the fault current within a specified time period, before the fault current can cause excessive heating or damage to equipment. In addition to calculating the fault current, It's also important to consider the coordination of protective devices in the electrical system. Protective device coordination involves selecting and setting the protective devices so that they operate in a coordinated manner to isolate the faulted section of the system while minimizing the impact on the rest of the system. Proper protective device coordination can help to prevent cascading failures and ensure the overall reliability of the electrical system. The calculation of fault current is an important aspect of electrical system design and analysis. By accurately calculating the fault current and coordinating the protective devices, it's possible to protect the electrical system from damage during a fault and ensure the safety of personnel and equipment. Remember that short circuit calculations can be complex, and you should always consult a qualified engineer. Always prioritize safety when working with electrical systems. Never work on live equipment unless you're properly trained and equipped. Always de-energize and lock out equipment before working on it. Always use appropriate personal protective equipment, such as safety glasses, gloves, and insulated tools. By following these safety precautions, you can minimize the risk of electrical shock and injury. It's also very important to regularly inspect and maintain electrical equipment. This includes checking for loose connections, damaged insulation, and other signs of wear and tear. Regularly scheduled maintenance can help to prevent electrical faults and ensure the safe and reliable operation of the electrical system. When working with transformers, it's also important to be aware of the potential hazards associated with transformer oil. Transformer oil is a dielectric fluid that is used to insulate and cool the transformer. However, transformer oil can contain harmful chemicals, such as polychlorinated biphenyls or PCB, which are known to be toxic and carcinogenic. When handling transformer oil, it's important to wear appropriate personal protective equipment, such as gloves and respirators, to avoid exposure to these chemicals. It's also important to dispose of transformer oil properly, in accordance with local regulations. In conclusion, calculating fault current from nameplate data is a useful tool for understanding the behavior of electrical systems during fault conditions. However, it's important to remember that the formula is a simplification and that the actual fault current can be affected by a variety of factors. By considering these factors and consulting with qualified electrical engineers, you can ensure accurate and reliable results and protect the electrical system from damage during a fault. There are also advanced methods to calculate fault current, and they include using software for power system analysis. These software packages, such as ETAP, SKM, and Easy Power, can simulate complex electrical networks and accurately calculate fault currents at various locations. They take into account factors such as transformer impedances, cable impedances, generator contributions, and motor contributions. These software tools can also perform protective device coordination studies to ensure that circuit breakers and fuses are properly sized and coordinated to protect the electrical system. These software programs often use iterative methods to solve the network equations and determine the fault currents. The software can also generate reports and diagrams that show the fault current levels at different locations in the system. These reports can be used to select appropriate protective devices and to verify that the electrical system is adequately protected. In addition to using software, there are also analytical methods for calculating fault currents. These methods involve using mathematical equations and network analysis techniques to determine the fault currents. One common method is the symmetrical components method, which is used to analyze unbalanced faults such as single line to ground faults. The symmetrical components method involves decomposing the unbalanced fault currents and voltages into three sets of balanced components: positive sequence, negative sequence, and zero sequence. These components can then be analyzed separately using network analysis techniques. Another analytical method is the impedance matrix method, which involves constructing an impedance matrix for the electrical network and using matrix algebra to solve for the fault currents. The impedance matrix method can be used to analyze both balanced and unbalanced faults. The choice of method depends on the complexity of the electrical system and the desired level of accuracy. For simple systems, the simplified formula may be sufficient. For complex systems, software or analytical methods may be necessary. It is important to note that fault current calculations are based on certain assumptions, such as the assumption of a bolted fault, which is a fault with zero impedance. In reality, faults may have some impedance, which will reduce the fault current. Therefore, it is important to consider the potential impact of fault impedance on the fault current calculations. Fault current calculations are an essential part of electrical system design and safety. They are used to select appropriate protective devices, to verify the adequacy of electrical equipment, and to ensure the safety of personnel. It is important to perform fault current calculations accurately and to consider all relevant factors. It is also important to keep the fault current calculations up to date, as changes to the electrical system can affect the fault currents. Changes such as adding new loads, replacing equipment, or modifying the network configuration can all affect the fault current. Therefore, it is important to review the fault current calculations periodically and to update them as necessary. Another aspect is understanding the difference between prospective fault current and actual fault current. Prospective fault current is the maximum fault current that can occur at a particular point in the system, assuming a bolted fault. Actual fault current is the fault current that actually flows during a fault, taking into account the fault impedance and other factors. The prospective fault current is used to select protective devices, while the actual fault current is used to assess the impact of the fault on the electrical system. This involves coordination studies that determine the optimal settings for circuit breakers and fuses to minimize downtime and prevent damage to equipment. The goal is to ensure that the protective devices trip quickly enough to prevent damage, but not so quickly that they cause nuisance tripping. The coordination study takes into account the fault current levels, the time current characteristics of the protective devices, and the load characteristics of the electrical system. When performing fault current calculations, it's also important to consider the grounding system of the electrical system. A grounding system provides a path for fault current to flow back to the source, and it helps to protect personnel from electric shock. The type of grounding system can affect the fault current levels and the performance of the protective devices. Common types of grounding systems include solidly grounded systems, impedance grounded systems, and ungrounded systems. Solidly grounded systems provide a low impedance path for fault current to flow back to the source, which results in high fault current levels. Impedance grounded systems use an impedance, such as a resistor or reactor, to limit the fault current. Ungrounded systems do not provide a direct path for fault current to flow back to the source, which results in low fault current levels. However, ungrounded systems can be more susceptible to transient overvoltages. The selection of the appropriate grounding system depends on the specific requirements of the electrical system. Different types of faults can occur in an electrical system, including three-phase faults, single line-to-ground faults, line-to-line faults, and double line-to-ground faults. Three-phase faults are the most severe type of fault, as they involve all three phases of the electrical system. Single line-to-ground faults are the most common type of fault, as they involve only one phase of the electrical system and ground. Line-to-line faults involve two phases of the electrical system. Double line-to-ground faults involve two phases of the electrical system and ground. The type of fault can affect the fault current levels and the performance of the protective devices. Each type of fault has a different impedance, which affects the amount of current that flows during the fault. Three-phase faults typically have the lowest impedance, resulting in the highest fault currents. Single line-to-ground faults, line-to-line faults, and double line-to-ground faults have higher impedances, resulting in lower fault currents. The protective devices must be able to interrupt the fault current for all types of faults. The NEC or National Electrical Code provides requirements for fault current protection. NEC Section 110.9 requires that equipment intended to interrupt current at fault levels be rated for the voltage available at the line terminals of the equipment. Equipment shall be able to withstand the available fault current. NEC Section 110.10 requires that the overcurrent protective devices, the total impedance, the component short circuit current ratings, and other characteristics of the circuit being protected shall be selected and coordinated to permit the circuit protective devices to clear a fault such that the damage to electrical equipment is limited. NEC Section 230.95 provides requirements for ground fault protection of equipment. Ground fault protection of equipment shall be provided for solidly grounded wire electrical services of more than 150 volts to ground but not exceeding 1000 volts phase to phase for each service disconnect rated 1000 amps or more. The maximum setting of the ground fault protection shall be 1200 amps. NEC Table 310.16 provides ampacity ratings for conductors. The ampacity of a conductor is the maximum current that the conductor can carry continuously under specified conditions of use without exceeding its temperature rating. The ampacity of a conductor depends on its size, insulation type, and installation method. NEC Section 450.3 provides requirements for transformer overcurrent protection. Transformers shall be protected against overcurrent in accordance with their size and type. The overcurrent protection shall be provided by fuses or circuit breakers. The location of the transformer overcurrent protection depends on the transformer's primary and secondary voltages. Transformers also have inrush current. Inrush current is a high transient current that flows when a transformer is energized. The magnitude of the inrush current can be several times the transformer's rated current. The inrush current can cause protective devices to trip, even if there is no fault. To prevent nuisance tripping, it's important to select protective devices that can withstand the inrush current. Some protective devices have a time delay feature that allows them to ride through the inrush current. Harmonics can also affect fault current calculations. Harmonics are sinusoidal voltages or currents that have frequencies that are integer multiples of the fundamental frequency. Harmonics can be generated by nonlinear loads, such as electronic equipment and variable frequency drives. Harmonics can increase the fault current levels and cause protective devices to trip. To mitigate the effects of harmonics, it's important to use harmonic filters or to select equipment that is designed to minimize harmonic generation. In summary, calculating fault current is a complex process that requires consideration of many factors. These factors include the transformer impedance, system voltage, cable impedance, presence of other equipment, grounding system, type of fault, NEC requirements, inrush current, and harmonics. By considering all of these factors, it's possible to accurately calculate the fault current and to select appropriate protective devices to protect the electrical system.